I'm Katrina Murray. I'm a postdoc at CU Boulder, and I want to talk to you today about spot crossing events. So I'm glad that Annabella introduced this for me. So it's a long title, but essentially I just want to focus first on the impact of these spot crossing events on our transmission spectra, more from a simulation point of view. And then I want to go on and talk a little bit about the JWST program that I'm leading to try and measure the first intentional empirical panchromatic spectra of a star spot with JWST. Try saying that 5 times fast. So thanks to Ben and everyone else for introducing stellar contamination. We're already seeing this become a major limiter in the era of JWST for our planetary inferences. We're struggling to disentangle the transit light source effect from the planetary atmosphere. We're struggling with the discrepancies between our 1D stellar models as well as between those models and empirical data. But there's lots of cool work on progress that everyone has been presenting in this conference that I am excited for. And so we do have to worry about this because we are already seeing a number of spot crossing events happening in JWST. We are seeing it not only for our M dwarfs, but even for earlier and, I should specify that these are in prep, so please don't share these. I forgot to put the thing on there. Yeah, we're seeing them for earlier type stars as well, like K and G dwarfs as well. And so I'm interested in the question that Elizabeth Newton opened yesterday, which is, can we leverage these observations to learn about the star? And a big challenge with that is the fact that you have degeneracies. So that boils down to if you have a transit chord with a spot on it, there's a number of other spots that could give you the same signature in your light curve. So I've been, this is going to be a bit choppy, sorry. I've been working on trying to map the degeneracy space of these spot crossing events. So I have created, the caveat is that this is a pretty simple toy model using just basic kind of geometry. But essentially, I create a large grid of spot parameters, contrast, latitude, longitude, radius, and then I tie those to spot crossing observables. So I care about 3 observables here: the spot crossing epoch, the duration, and the size of the bump in the light curve. And in doing so, if we have a light curve with a spot crossing event, we can kind of work backwards and say, well, what range of spot parameters would fit those observables with some respective uncertainties? And so in each case here, I have a true spot, which is this black circle. I then create a light curve on top from that true spot, and then given those observables with some uncertainties, the orange region is the degenerate samples that would fit those observables. And you can see some trends start to emerge. Like, this is obviously quite a simple model. We're not taking into account the shape of the star spot crossing, but you're seeing that like the longitude here is pretty well constrained because it really just ties to the timing of the spot crossing, apart from at the limbs where it gets more complicated. We're seeing that the spot crossing duration can give us a lower limit on the radius, and the latitude remains fairly unconstrained. So we applied this to a real system, some real data from JWST, Jessica Libby-Roberts' program, GEO2571, observing Kepler 51d. And we see a spot crossing event happening in the middle of the white light curve. And so we took a reduction of this data, and we independently applied spot rod and starry to try and derive the spot parameters. And what you see on the right here is that we converge on vastly different spot parameters for this system. And so I was interested in then applying the degeneracy stuff I've been looking at to this system and say, are we fully exploring that degeneracy space? And the answer is, I think no. I think both using starry and MCMC and using spot rod and dynasty, we're only exploring part of that degeneracy space. And obviously we're expecting the degeneracy mapping to be a lower bound, but I think it is a concern that we are not, even using these sampling methods, we don't seem to be fully exploring that space, meaning that our posteriors and the uncertainties on our posteriors for those parameters are not meaningless, but they're not representative of the true situation. And so the good news in these cases are that the contrasts for both methods, despite vastly different spot parameters, do agree. And the degeneracy limits that I find from just mapping are kind of outside of the posterior regions in all cases. But this is a sun-like star, so for M dwarfs, things might be more difficult. So then I wanted to say, well, given that we have these degeneracies, and given that difficult to know what to do with them. If we have a single spot crossing event in a light curve, can we recover the spot parameters based on what we know we've injected? So I created a sample of 1,000 spot crossing events with various parameters. I injected those into light curves with varying levels of noise, and then I saw what I could recover using optimizing starry best fit models. So here on the right, we have the injected on top, the resulting light curve in the middle, and then the recovered on the bottom. And you can see that the results pretty much follow along the lines of the degeneracy I was talking about. So we're constraining the longitude very tightly, the latitude not very well at all, and the contrast and the radius okay. So about 3 to 5% on average difference between injected and recovered parameters here. We are recovering the radius of the planet and the transit depth fairly well. So I think this opens this question about whether we should be masking or modeling spot crossing events in our light curve. I see both approaches in the literature, and don't come for me, I think they're both valid. I just think they have assumptions. And so if you have a spot on your star, you're going to have some contaminated depth due to the transit light source effect that we know about. If you mask that spot crossing event, you're just going to recover that contaminated depth. So usually what we then do is we fit in the transmission spectra, we fit for the contamination as a function of the spot coverage fraction and the contrast spectrum, which I think usually requires us to assume some contrast spectrum based on 1D stellar models. And if we model it, we may be able to recover the true transit depth, but that's assuming that we're modeling it well, which if we have degeneracies can be a hard thing to know. So within our injection recovery framework, we find that over 95% of our more significant cases, we improve by modeling compared to masking. That's maybe not too much of a surprise, but we have our recovered depths on the y-axis and the injected on the x, and then if we just masked, we get that kind of gold line there. The only cases within our framework where we don't improve are for small contaminations, so less than 3%. And here, we find that we are overcorrecting for the transmission spectrum, for the transit light source effect. And these are our 5 worst recovered cases, essentially, and you can see in every case we are injecting something quite small, actually at the limit of our parameter space, and we're recovering something sort of larger and darker. And in each case, we see that the injected and recovered light curves look kind of the same. So I think we're pushing against the degeneracy space here. But we're also pushing against, specifically for starry, where starry doesn't do well with small spots. So we're kind of pushing against starry's limits here as well. And so for another method like spot rod, you might not have that 3% cutoff. And so you might then ask about unocculted spots, because I haven't talked about that yet. So it's kind of the same as before. If you mask, you're going to get that contaminated depth. And if you model, you're only going to correct for the occulted part of the heterogeneities. So you're going to go some of the way to correcting that depth, but then you will have to fit, but what you have to fit for is the difference in spot coverage fraction between the occulted and unocculted surfaces. So it's only one parameter, and we don't have to assume any stellar models. I'm going to skim over this because I'm running out of time. But so just for the last part, I want to touch briefly on the GEO 5863 program that I'm leading to try and observe TOI 3884b, which has this big spot crossing event, to try and build up an empirical spectrum of a star spot with JWST. This is very much preliminary work, so please don't share. So Jessica introduced this system very nicely on Monday, so that saves me some time. We have a large super Neptune-sized planet around a fully convective misaligned M4 star. It is quite a uniquely observable cool atmosphere. It's got a temperature about 440 Kelvin, I think. And so with these kind of whopping large features, we should be able to look into some cool chemistry here. We also have this persistent polar spot complex that we're seeing in every transit. And so our hope with JWST was to kind of build up that spot signature and be able to then empirically derive the spectrum of the star spot. Doing that can then help us compare different benchmark strategies for cell contamination mitigation, as well as compare with theoretical MHD models. So we were awarded 4 transits with JWST, 2 with NIRIS, and 2 with NIRSpec G395M. And then we got those observations in December, so Yeah, spoiler, you're not going to see a spectrum today because it's just too soon, but we do have some light curves from the system. So I'm sure you're all thinking like, wow, what a nice spot crossing event. But we're also seeing a lot of flares. We're seeing strong H-alpha emission from our flares. We're seeing the hydrogen Paschen lines in here, as well as a lot of other fun things going on. We got simultaneous ground-based observations with this JWST transit and from LCO and APO. And you can see that in green and red passbands, we get much larger flare amplitudes, as well as the flare is extending quite far into our transit, which is going to be extra fun to try and disentangle the flare, the spot, and the ingress of the planet all at once. This is one of our near-spec G395M observations. We are also seeing flares in the near-spec band, as well as a night spot crossing event here as well. So two of the big things that we're dealing with right now are we are seeing different spot structures in every visit. These are 4 consecutive transits, 4.5 days apart. So we are, they are significantly different even within the same instrument. So we are going to have to try and disentangle maybe the rotation of the star and how those spots are rotating around the pole, as well as all of our flares are nice, complex combinations of flares with interesting morphologies that are happening at inconvenient times. So, how to disentangle the flares from the spots and also from the planet itself is going to be, one of the big challenges we're working towards. And I want to plug that there are 3 more observations of the system coming in May, June with the GEO 5799 program, PI Leonel Garcia. And so with those observations, 6 months taken apart, we might be able to disentangle not only the rotation of these spots, but also maybe the evolution over time, if we can get a good model on that. So I'll just leave my conclusions up since I'm running low on time. Thank you very much.
Right on time. So what questions do we have? Oh, right. Yeah.
Hi, could you go back to the one of the earlier slides where you talked about having challenges with sampling the spots?
The Kepler 51 example?
Yes, I think so. I think it might have been before that as well.
This one?
Yeah, that one. Yeah, so one of the difficulties with Starry is that you can't model very small spots, but
Yeah.
the advantage is that for certain assumptions about the spot properties, it should be analytic. So have you tried using the sort of analytic framework of Starry to see how the degeneracy looks?
No, I haven't yet. I've only done what I've presented here, and then Jessica applied spot rod as well. No, but it's something to look into. Thanks.
Hi, that was awesome.
Thank you.
Is there a way of knowing if the planet crossed the flare?
Yes, probably. It's too soon, I think, at this point to tell because we have these like 3 sort of almost degenerate issues. But I think we will see because we have strong H-alpha and hydrogen lines, I think that if we see them disappearing, it is possible because if we assume the flares are coming from this big spot complex that we know we're occulting, it is possible that you could localize the flares there, but we're not seeing anything so far, and I think it's too early to say. But we're definitely going to be looking out for it, whether like the H-alpha disappears as we start the transit. But yeah, nothing to report yet.
Thank you.
Hi, cool work. What's the smallest or least contrast spot that you would need to worry about that would have an impact on your eventual transmission spectra?
That's a good question. I wouldn't know without modeling it directly. We put a cutoff in the injection recoveries with Starry to 5 degrees because Starry, you need a large number of spherical harmonic orders to model that fine of a resolution on the surface. And so we weren't going really small with Starry. We did find for the 3% contamination, it depends on what your other uncertainties are in transmission spectra, whether the you know, a 3% error in the transit depth is significant or not to what you're trying to find. But we didn't go any smaller than that, so I don't think I could put a number on that.
Cool, thank you.
Let's thank Katrina again.